Okay, so I kind of want to wait until everyone's here, but I mean, we don't have that many people anyway. So like what I said in the announcement, so since we lost kind of one class on Tuesday, so I'm thinking about make up the one we lost, and especially the after we finish up the chapter 1 today, the next chapter, like chapter 2, is actually should be familiar with most of you who actually took the curve and surface, because then essentially we're going to talk about a smooth map or smooth function, and essentially the definition we are going to use is pretty much exactly the same when we talk about smooth function from a regular surface. So this should be a more or less a familiar topic for everyone. So I hope that I mean, once we pass the this chapter 1, I hope like at least from chapter 2 from now on, it should be like more familiar, at least for chapter 2. Okay, so regarding the time, so as I mentioned in the email announcement, that I'm thinking about making up uh, the the lecture on during the weekend. So right now I could think of two options here. So either they're more or less the same, to be honest. So either if people prefer to watch me live during the lecture, then we can do a live Zoom lecture like what we usually do over the weekend, for example, maybe Saturday afternoon. Or if no one want to come, for example, that no one can really find a time, or you guys don't prefer live, then I can just make a recording and then post it like over the weekend, something like that. So now I want to do a inform. So for those, if some of you want to do live, then I will try to find essentially a common time where most people can make it. And for the people who don't want to make it or who cannot make it, you can definitely watch the video later on. So so basically, can anyone give me a signal, or like just type in a message if you could? Let me know which one do you prefer. Do you prefer live? Okay, Saturday. Is Saturday okay? Like, just give me an option. For example, someone prefer live or just recording. Give me an option. You can type it or you can directly tell me, because I need people response. So okay, so someone do recording, and someone, most I see 3 live, 1 recording. I think we still have more people. Who didn't, who say either will be fine. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We should have. Oh yeah. Okay. Yeah. So okay. So yeah. So if so, I know that some of you may not be able to make it. So most of people are fine with live. Okay. Then would Saturday afternoon, say the same time from 4 to 5:15 works? Does anyone have a strong objection about Saturday afternoon? Or if does anyone cannot make it, that rather move 4 to 5 to maybe a little bit earlier, something like that. So 4 to 5 works. Okay, so I don't see the objection. Yeah. Okay, so I'm going to do oh, I see. Okay. So then I think so. Okay, so then I'm going to make announcement after today's class. So right now, I think Saturday afternoon from 4 to 5:15, pretty much the same time as the usual lecture time work. And as I said, because I know this is a makeup thing, so if like for whatever reason that because you have some arrangement already for Saturday, I mean, you don't have to come. As I said, this is a makeup things that because we already lost 50% of the whole week. So, and I really want to get to the chapter 2. So I appreciate that you guys want to can accommodate this. And so I'm going to make an announcement later on. So we're going to put it on Saturday from 4 to 5:15. And as I said, right after our makeup lecture, I'm going to post the recording. So and then like for whoever cannot make it on Saturday, you can definitely watch it But as I said, the arrangement would be like then coming back next Tuesday, I'm going to talk about the material after the one I'm talking on Saturday. So if you miss the Saturday one, then you have to kind of make it up, hopefully before the Tuesday. So everything is kind of like connected. Okay. Okay. So and another thing is that I know this is kind of tedious, and I actually already changed my office hour once. So I know that some of you actually have class from 3 to 4 Monday and Wednesday. And I just realized I double checked another office hour schedule, and apparently there's also a functional analysis has office hour Monday and Wednesday until 3:20. So what I'm going to do is I'm going to move the office hour again. Sorry about that. Like, so right now I think it's
Professor,
yeah, sure.
I have a problem, a big problem, in fact.
Oh, so what's the problem for the office hour or for the
for the office hour, both timings, I am after the class, exactly after 15 minutes, I go uh, uh, to my class I am teaching. So even if it is so, our office hour is Monday and Wednesday.
yeah. So you mean that when
So
are you
I
going to
am.
teach?
Oh no! In both cases, I am finishing 3:45.
Uh-huh. And then you say you're teaching at when? 5:15?
So sometimes this 1 hour is not after I just go, after I finish the class in 3:45. I just get out or something. So I don't know if it's available to do it something like Tuesday, maybe at the morning, or by email. I can send you an email for specific office hours or asking appointments.
Yeah, sure. That's definitely. So I'm a bit confused. So you said that either 3 to
No.
4.
My classes are, I am teaching on Tuesday and Thursday. So I'm not teaching on Monday and Wednesday.
Oh, okay. So
But I have a class. I think some of the students have it from 2 to 3:40, no, 2:30 to 3:45. And sometimes I don't attend after this 1 hour, your office hour.
okay, so I'm a little confused. So
Is
you
this clear,
can
or I'm not?
so,
Okay.
the internet is
So this is the
a
case.
little bit
In
like
Monday,
disconnect.
so on Monday and Wednesday, I have classes from 2:30 to
Uh-huh.
3:45.
Yeah. Mm-hmm.
You changed, so you added 1 hour. So you said you will be available from 4 to 5, but even sometimes I don't come in this 1 hour. It says
Oh,
after the class.
okay. So it
So
because you have
I
other
was
courses or
if
because
possible
you're
in the. No, sometimes I just go out or do something. I might be busy sometimes, so I cannot do it.
okay. So I mean the things that I cannot like fit everyone just because you like I mean I'm trying to already fit everyone. So the things that I'm trying to find the best option for majority of people, but I cannot guarantee that everyone I can fit everyone's preference. So right now my original office hour is like right now, like for now it's Monday 4 to 5 and then Wednesday 3 to 4. So I was actually thinking moving this 3 to 4 to 4 to 5 as well. So whoever has class until 3:45 can also make it. But the thing is that like I also have other, I mean, I know that people usually have more other things earlier. So I think, in my opinion, putting at 4 to 5 for both of day can fit most of people, especially for people who actually have class or office hour, some other office hour earlier. But yeah, that's the best I can do. And if you really, really cannot make it all the time, that's fine as well. I mean, you can send me an email to make an appointment. But of course, I mean, you need to tell me a little bit earlier so I can react. Yeah. Is that okay?
Yeah, that's okay. Yeah.
Yeah.
For me,
Okay.
actually.
Yeah. Yeah. I mean, the things that I know that's not the best for everyone. Like sometimes you have something to do. I'm not forcing everyone to come to the office hour, of course. But if you know that in advance that you will have something coming up, and then I mean the things that like if you can make it, try your best to make it, right? And then if you can't, and you already knew that you're going to have something pop out and or have some issue like with for the office hour during that week, then just send me an email like earlier in advance. So I mean, we can set up appointment. Or as I said, I mean, I know Tuesday, Thursday, we're going to have a class, and maybe like either you can ask me after the class, or if you couldn't, then as I said, just send me an email in advance so we can set out the time. But of course, I will try to focus on the office hour, because I mean, I would not be able to always say yes to the extra appointment, because I also have some other, probably some schedule issue. Okay, so I'm going to change the office hour, everything to be on Monday, Wednesday, 4 to 5. So at least for people who have class until 3:45, then you can make it. And then, yeah, as I said, I know that this may not fit every single person's preference or schedule, but try your best to make it, okay? And I think that's it. I don't have any other things. So yeah, let me just write down. So Saturday, 4 to 5, 15, right? And this is the makeup thing. And as I say, if you cannot make it, that's fine. I will just post the recording. So this is live. Okay. Okay, so yeah, so let me know. I mean, I know that the live Zoom, like sometimes the internet is not perfect. So sometimes you see that my reaction is very slow because I could not hear very clearly. So if you have any question you think of, just email me. I mean, I know the online teaching is not ideal, but I'm trying to make the best accommodation. Yeah. So okay, so I'll go today. So what we're going to do is I'm going to give you a bunch of examples, and I can tell you right now, all the example are like, you can find it in the textbook, but some of them actually are a little bit not clear, like some of the detail. So I want to just explain a little bit, but most of, like all of them, you can find it in the textbook. So this means that after today's class, you should definitely go read through the textbook, that they have actually provided so many nice examples for smooth manifold. So actually, I haven't seen any other books that provide such many, like this many examples. So you can kind of take a look, and actually we're going to see some of the example over and over throughout the whole semester. And then after the example of smooth manifold, then the last topic, which I'm going to do it very quick, is the manifold with boundary. So we actually right now you can see that always all the manifold we work with is locally Euclidean to Rn, right? So Rn essentially is kind of like you don't see any boundary, right? It's kind of just infinite large. You don't see an n here. But of course, that you can think of a lot of example where you like your geometric object, your space has a boundary. For example, cylinder, right? When I say cylinder, I mean the one truncated, right? Or actually the upper half plane, right? Your upper half plane will stop at the, say, y equals 0 or xn equals 0, right? So there's a boundary there. So we're going to see how do we define either a topological manifold with boundary, or we can actually on top of that give it a smooth structure. Then we can define the smooth manifold with boundary. Then we're going to see like how we make sense of those structure. But keep in mind that it's going to be very similar to what we have seen before. The only difference is that back then the topological manifold is locally Euclidean, meaning you can always find for each point, you can find a neighborhood of this point, which is homeomorphic to an open set in Rn. But for the case for manifold with boundary, then you might have an open neighborhood which is homeomorphic to some open set in upper half plane, upper half space, Hn. Okay, so that's the only difference. And then the remaining definition is pretty much the same. That's why I'm not going to go into too detail about it. You can definitely read the book and see like everything is pretty much the same. Okay, so first example, let's see. So I mean, this is kind of like a trivial example, but I think this is going to help you on like some of the homework if you're still not knowing how to do it. So of course, like the easiest example of smooth manifold you can think of is the Euclidean space itself, right? And so, I mean, Rn we can do for any n beta equal to 0. We can even talk about R0. So you might not see R0 that much, but when we talk about R0, we just means that like a set of countable discrete points, right? Because you need to be second countable, so you can only have countable many of them. So R0 usually means just a bunch of points, but countable many. And we can define a standard smooth structure on it. And when we say standard one, it's the one that determined by the atlas of just single chart, right? That's the easiest chart we can think of, meaning your open set is just the whole Rn, right? No one stop you from taking the whole open set, whole Rn. And the homomorphism is just identity map from Rn to Rn, right? That's kind of like a trivial thing we can do, we can think of. And because it's only have single chart, so I mean, you don't even like, there's only single chart, so you don't need to check whether it's smooth compatible with other. Then this single chart is an atlas, and it's by itself a smooth atlas. So once you collect all the possible other smooth compatible charts, then that will give you the smooth structure you want, right? So let me remind you what's a smooth structure. So first you have a bunch of coordinate charts, right? That give you the atlas. Then you need to check whether in between all these charts, whether the transition map is a diffeomorphism or not, which means you're checking whether mutually they're smooth compatible or not. If yes, then this collection of charts this atlas is the smooth atlas. Then now in order to define smooth structure, then you want to find the maximum one, right? Smooth structure essentially means the maximum smooth atlas. So that means you might have some other charts out there which you haven't collected, and it's possibly those charts still smooth compatible with the charts you already have. Then you need to include it in it. Once you include until you cannot include it anymore, then that's the maximum smooth atlas we are looking for, and that's what we call the smooth structure. So in this case, you can see since you start with the atlas of just one chart, right? So you say, okay, what would be my smooth structure looks like? So you essentially want to find the maximum like collection, right? So you want to include all other charts which is smooth compatible with this single one. So you can think about it. Whenever the domain intersect your open set, then you need to check whether the transition map is smooth or not. If it's smooth or diffeomorphism, to be precise, you collect it, right? So you can see that then in this case, what you need to include is all the possible charts like this, where U is any open set, right? Because if U is any open set, it's going to intersect Rn anyway. So then if it intersects, then you're going to see, okay, is there any, is the transition map, it's going to be diffeomorphism. It turns out that if you have an open set U and then you have a diffeomorphism phi from U, then phi and identity is going to be smooth compatible, right? Because you can definitely check that either this or identity over this, it's either this two, it's going to be smooth, right? So it's a diffeomorphism. So basically it tells you that you need to collect all such charts to include in your smooth atlas to form the smooth structure. So basically, because the standard structure is so easy, I can tell you that the standard smooth structure on Rn contains all possible charts like this, where U is an open set and phi is a diffeomorphism from U, and that's it. That's what we call the standard smooth structure, determined by this single chart. Okay, that's the standard one. But of course, you can ask the question, is there any non-standard one or something different, right? So I'm going to give you this example, which tells you that there exists a non-standard smooth structure on Rn. So I'm just going to use R1, for example. So I can actually find some other different smooth structure. So the different one is going to be determined by the following another single chart. So we consider another atlas of single chart on R, right? So I only consider R1. And this time my homomorphism is going to be per psi, where per psi is actually S cubed, right? And we can actually check that this chart is not, this is not C infinity compatible with the standard one. So standard one in this case is the whole R and the identity map, right? Because you can actually directly check if you check the transition map, you take the identity and compose with the inverse of this psi. You can check it's going to be y to the 1/3, right? And 1 to the y/3 is not smooth at the origin. So this means that whatever the structure, smooth structure determined by this psi would not be compatible with the standard one. So they should be two different structure, right? So essentially, I remember one of the homework question asked you to check whether two atlas determine the same structure. Then all you need to show is that all the charts in each smooth atlas, if one of them is compatible with the other, then it has to be contained in the same smooth structure, right? And this example is the opposite situation, right? You can see that this psi, another single chart psi is not compatible. So when you form the standard smooth structure, this psi will not be in it because it's not compatible with it. So which means that they determine the different structures. So they determine, or you can say they defined different smooth structure. So indeed, we can find something that's different than the standard one, right? And this also shows you that smooth manifold may have different smooth structure, okay? But most of the time, if it's not necessary, we would just say, oh, this is a smooth manifold without specifying which smooth structure we use, unless we need to do something more detailed. But you can see that there's might be more than one smooth structure we can put. Okay, and another typical example is the example 1.26, where this is actually also quite intuitive, and we are in some sense keep using it. So now let's say we have a smooth manifold to start with, right? M manifold means it's n dimension. Okay, let's say we already know M is a smooth manifold, and we have an open subset U. Okay, and it turns out that we can right away know that U itself is another n-dimensional smooth manifold, and it has a natural smooth structure in some sense inherited from this ambient space M. Okay, because U is a smaller open subset, right? And I can tell you the smooth structure coming from M can be defined as the following. So as long as I can give you a smooth atlas, then I'm done, right? So first, I can tell you that at least I can first find an atlas, right? Before I check the compatibility. Then the atlas, I called it A sub U, is the following. So what would be the open set? Then I essentially collect all the possible open set in this format, and V, where V looks like some intersection of an open set W with my open subset U, right? So it's like you have so let's say if this is a big picture, like rough picture, M is your manifold, and you have an open subset U, right? So how do you form the correct atlas? So you find that, okay, I already have atlas in M, right? So I will have all this open set, right? W. So if this is W, then I just take the intersection, right? Because then W intersect U would be open in U, right? This is a subspace topology, right? And this W essentially come from the atlas, that smooth atlas we already have from M. And the phi here is the one of the smooth coordinate map from the bigger space M, right? So once you do this kind of intersection, and your map here that the diffeomorphism or homeomorphism you need is essentially you take phi restricted to a subspace, like subdomain V, right? So you can actually easily check that all this should be smoothly compatible with each other, right? Because you can imagine like as a in bigger domain, it's already smooth compatible. All you did is kind of just restricted in a smaller domain. So of course it should be smooth as well, right? So you can easily check, I'm not going to do this. This is very routine. So we can actually check that this atlas on the open subset is a smooth atlas. So then if you once you have a smooth atlas, then you can put the smooth structure determined by this atlas. Then by itself, U is a smooth N manifold, right? Because you have a smooth structure on it. And on top of that, with this particular smooth structure coming from the ambient space, U is what we call the open submanifold, right? Actually, you're going to see later on, I'm going to show you a bunch of like example, which is essentially an open submanifold from some other bigger manifold. Okay, so essentially this is give us a very nice like criterion, right? You can actually easily create much more smooth manifold, right? So as long as you have an open subset which lies in a smooth manifold, then that open set will still be smooth manifold. So you can think of a lot of example. For example, let's say the ambient spaces are to the n+1, and you have an open ball, right? An open ball is an open subset in R n+1. So open ball should be a smooth manifold, right? So any open subset you can think of a smooth N manifold is another smooth N manifold. So there's so many examples you can create it without even checking it. Okay, so another example, which this is a little bit more involved, this is the one I want to spend a little bit more time on it. So even though the textbook didn't put too much of the detail, but I think it requires some explanation. But I mean, the thing is that like intuitively, it's actually very straightforward. But I want to provide a little bit more explanation, like hoping to like rigorously convince you that why this is the case. So, but later on, when you see that how I identified this vector space with Euclidean space, you will see that why this should be true. So another example of smooth manifold is any finite n-dimensional real vector space. Okay, so this is quite general, right? So first of all, real vector space means that when you multiply, do the scalar multiplication of this vector space, the scalar you can multiply is real number. You might have some other type of vector space, maybe complex or any other thing. But here I only deal with the I mean, just to be simple, we deal with the real one. And we want to have finite n-dimensional vector space. If it's infinite, there might be some issue. So it's not always true. Okay, so I mean, vector space, if you don't know, please check the appendix or the linear algebra. This is the usual vector space. First of all, you need to be close under scalar multiplication and addition, and it satisfies some of the algebraic rules. And then once there's some like, I don't know, 8 axioms that you need to check. But usually all the nice space, for example, typical vector space, you can have space of matrix, right? Or Rn is another simple vector space. Or you can have like space of like polynomial of certain degree, up to certain degree. Those are finite n-dimensional real vector space. So the first thing we know, actually, I'm not going to prove it because it's quite involved, like any norm, if you can put a norm vector space, then it's going to give you a topology. I'm going to explain in a minute why this is true or what kind of topology is this. And once you define a topology, this particular topology turns out to be independent of the choice of norm, which basically means any norm you put on such finite n-dimensional vector space is going to define the same topology. And you can actually prove it. The one of the reasons you can explain is that because those norms are actually equivalent. Okay, so let me explain a little bit more words that how do we use a norm to define a topology in this case, right? So basically, let's say we have a norm, right? So once you can define a norm on V, right? This is a little bit, I don't know, like in like advanced calc or I mean linear algebra, we also talk a little bit about it. Once you have a norm, you can define a metric. In some, actually norm is stronger than a metric, right? Then once you have a norm, you can define a metric, right? Or in some sense, you can say it's a distance, right? once you can define a metric, then automatically you can define open bowl. And this is the, so what do we need for an open bowl, right? You need to describe, so open bowl, let's say open bowl center at certain point, then you essentially collect with radius r, for example, you collect all the points that has the distance to this center within the distance with the radius r, right? So the distance, the radius r here that we need to define, we're going to use it the sense of metric or distance, right? Before you can define distance, you cannot talk about open bowl because you don't, it doesn't make sense to talk about distance, right? Once you can talk about metric, once you can define a metric or distance, you can talk about open bowl, right? Once you can define what's an open bowl, you can make sense of open bowl, then you can create what we call the metric topology. You probably, when you read the appendix, you probably already see people use this metric topology to define the standard one on the Rn. So what's metric topology, right? So let me put it down here. Okay, so metric topology, I think is the one that people are actually more familiar with in the analysis class. So it says that a set in V is open if for every point in this set, you can find an open bowl center at this set, right? And such that it's going to contain in the subset S, right? This is actually, I think, the if you know a little bit topology from the advanced calc like class, then you're going to see this is usually the definition they use. And you can actually check this way of defining open set should still satisfy the original definition that we use for defining a topology. That they're compatible, the definition are compatible with each other. Okay, so this way of defining open set is what we call the metric topology. Okay, then now we keep in mind, so now if you can have a norm on vector space V, then you essentially create a metric topology. Okay, so now to see that why V actually has a nice behavior or structure is because we essentially can identify such vector space with Rn when n is essentially the dimension for your vector space. Okay, so to do that, we're going to use the basis of this vector space, right? We know that for vector space, we can pick, for n-dimensional vector space, we can pick a basis consists of n vectors, and basis is not unique, right? So later on, we're going to see for different bases, it's going to be the same anyway. So for each basis, and you can see that this time I'm going to use this weird notation. So I'm instead of V1 to Vn, usually like I'm trying to be consistent with the textbook. So you're going to see that people will use sub-index for a vector. Okay, so I call this n vector. I mean, it's one of the bases I pick for the vector space V, right? Once with one particular basis chosen, then I can define the so-called basis isomorphism. Okay, so what's isomorphism? Isomorphism, the definition is essentially it's a bijective linear map between two vector space. Then it's isomorphism. Okay. So now I'm going to define isomorphism in the following. And it turns out that this is going to be our chart that we're going to use because it essentially, in some sense, identify your vector space with Rn. That's why, in some sense, we don't distinguish it sometimes. So the isomorphism, the basis isomorphism is defined. I mean, it depends on how you define it. You can define backward from vector space to Rn, but I'm just trying to be consistent with the textbook. So this time I'm going to define E from Rn to the vector space. Okay, And I'm going to define it as, okay, so you plug in any point in Rn, right? So let me rewrite it. So any point in Rn has n coordinate. Okay, then what's your output, right? Output should be in a vector in a vector space. So the way we identify it naturally, you can think of is that I'm going to take those n coordinate as my coefficient of the linear combination of the vectors, right? So I'm going to do this. So I'm using this coefficient as a coefficient for a linear combination of my bases, right? Because we know each vector in a vector space can be written as a unique linear combination of a chosen basis, right? So basically you can see that this, the right-hand side, the output would be a vector in V. And you can easily check because it's a basis, right? So there's a one-to-one correspondence with a vector and its coefficient, right? Essentially, this is usually what we call the coordinate with respect to particular basis, right? So this way of defining it is definitely a bijection, one-to-one and onto, right? And actually, you can easily show that the inverse exists because inverse is just kind of do it backward, right? So if you have any vector, right, in V, and you already chose this particular basis, E1 to En, right? And so you know any vector V is going to be written as a linear combination of EI, right? Then you essentially, this inverse just tells you, okay, you map this vector back to its coordinate, right? So in some sense, you can see that that's why a lot of time we can, in some sense, just forget about the basis and thinking of we are actually working in Rn in some sense. If you think about what you have done in linear algebra a while ago, a lot of time, the reason we can do all this nice computation is because essentially a vector space can be identified with Rn. So you can see that now this is how we identify a vector space like V of n dimension with Rn, right? So with this identification, then the norm we define on this vector space or the norm we choose will somehow induce another norm on Rn, right? So using this is maybe a little bit abstract, and this is not in the textbook, but I just kind of want to just do a little bit more explanation. So using this identification, the norm on V will induce or introduce another norm. Let's call it norm sub V in Rn. Right? Because you, in some sense, you use this isomorphism to define to identify both Rn and vector space, right? And remember, we already have a pre-existing norm on V, right? So you can use this, and then by the identification, you can essentially somehow create another norm on Rn. And the reason I do this new notation is because this norm may not necessarily be the same as the usual norm in Rn, right? Because you can put another so many different norm, one norm, two norm, I mean, so many different type of norm as long as it satisfies the definition of norm, right? So this norm coming from the vector space may be different than the one in Rn. So for example, so essentially you can compare with the standard one, right? With the usual Euclidean norm. And when we say the usual Euclidean norm is basically just taking this is what we call the true norm, right? The one that we're familiar with, taking the square and then take the square root, right? So one type of norm, like if you think about it, what's the possible norm, right? So once we define a norm, we can define an open bowl, right? So I'm going to just give you like a quick rough picture here. So this is the Rn, right? So let's say your norm coming from the vector space V. Once you have a norm, you can create open bowl. But your open bowl in that norm from V may not be the bowl that in in the usual sense, right? So for example, for Rn, what's the typical bowl looks like? It's really like round, right? That we know of, right? This is usually what we call some open bowl, right? But with the norm coming from V, it's possible, for example, that your open bowl actually looks like a square, right? I think if you take one norm or maximum norm, one of the norm, it's going to give you a square, right? If you say collecting all the points which has the distance to the origin, like a fixed distance, right? Then you're going to have an open bowl. So you might actually have a weird shape as your open bowl with respect to some other different norm. But I claim it doesn't really matter which norm I'm using, either the norm coming from the vector space or the usual Euclidean norm. They are going to create the same open set. Once you collect all this open set, if they create the same open set, they're going to create the same topology. That's why at the beginning I said any norm is going to create the same topology. It's independent of choices of the norm. So let me first write down this, and I'm going to explain briefly why they define the same open set. So these two norms define the same open set, and this define the same topology. Okay, so the reason is, okay, think about, go back a little bit. Let me push it a bit back. What's the metric topology we use here, right? Coming from the norm. We said that the definition is a set is open if for, so this is here. Let me just circle this. So a set is open if for every point in the set, you can find a smaller open bowl with respect to the norm, which contain this point and then also lies completely in the set. Then this set is called open. Okay, now I'm going to show you my, if you're talking about the, let's say the square is the one, the open bowl for the V norm, right? And the usual bowl is the one for the Euclidean norm, right? I'm going to say that either one is going to be open with respect to other norm. So for example, for each point in my, okay, I'm going to use the like not the dot line because otherwise it's not clear. So for this blue open bowl, right, for each point, you can always find an open square containing this point, right? And it's actually completely in the blue bowl. So this tells you that the blue bowl is open in the V norm sense. And vice versa, right? For any square, right, open square, that's the open bowl with respect to V norm. For each point in the square, right, either big or small, you can always find a smaller bowl, like the round bowl, which contain this point and also lies in the square. So it tells you that for the square open bowl, square bowl, it's also open in the sense of the other norm. So you can see that that's why, in some sense, you can also say that they will define the same open set anyway, because my blue bowl, in the eyes of the other norm, it's open, and vice versa as well. That's why all the open sets are going to be the same. And if all the open sets you define are the same, then what's topology? Topology is collection of all these open sets, then they're going to have the same topology. So they have the same topology anyway, so we don't distinguish it. Okay, so once they have the same topology, you can check it's going to be a n-dimensional topological manifold. And the homomorphism is exactly the E map, the isomorphism here, right? Because if you think about it, through this identification, we are going to define the same open set, right, for both V and Rn. So if they're going to map one open set to another or vice versa, so by how we identify it, this E, this map, or this isomorphism E is going to be our homeomorphism. So essentially, this tells us that E and E inverse is a homeomorphism or are continuous. So this E is going to be a homeomorphism. So that's our chart. So the chart we have, we can actually pick the single chart for this vector space. And E inverse is our chart for V, okay? And I'm not going to go into too much detail. You can check that V is a topological manifold, right? And then actually to be more precise, topological manifold of dimension n, right? Exactly n dimension. So now the question is, how do I find or give a smooth structure, right? What would be the smooth atlas? So the question now, the natural question is, what if we pick a different basis? Would that create something which is not compatible, right? So a lot of time you want to be careful when you work things with a coordinate or work things with bases. If you want to have a nice property or structure, you want those property to be independent of the basis you choose. Or later on, you're going to see like sometimes we want to be independent of the coordinate. Okay, so in this case, I want to really make sure that even I use different basis for this vector space, the atlas, the chart I create here is smoothly compatible. Okay, so now let's see. So I'm going to choose another basis here. So for any other basis, doesn't matter which one. So for any other basis, and let me call it E1 delta, E2 delta, En delta for B. I can also do the same basis isomorphism. Right, but now you can imagine like the basis is different, right? So the corresponding coordinate might be different. So, but the way we define is the same, right? So you define so you again have the same type of isomorphism. Okay, I need a little bit more space here. Okay, so once we have that, then now we need to do what we call the change of basis, right? This is something we learned in linear algebra. So we know this is actually from now on it's in the textbook. I'm just kind of like do the explanation here. So for each vector, right? This vector EI, this one of the bases EI, can be written as a linear combination of all the EJ delta, right? You can represent one vector in terms of linear combination of another basis, right? So for each I, you have this. And this AJI is essentially your transition matrix. And it's invertible because it's transition matrix. Invertible transition. Okay, so once with this, we can actually find the relationship. How do you change from one coordinate with respect to one basis to another? This is essentially the change of basis kind of review, right? So I want to check the transition map between two charts. Right, one is coming from the chart defined by E1 to En. The other is for the delta one, right? So I want to check the transition map. Right, so if you call the transition map is like this, right? Then you can see, okay, so for each vector, if you have some linear combination under one particular basis, it should be the same vector. So you can actually use represent it in terms of other bases. Then I'm going to just rewrite this EI by the formula here, do the change of coordinate. This may not be necessarily the same way as what you usually get used to, but there's so many different ways to divide this. Let me just put it as a same summation, it's easier. So I'm adding sum up I and j. So I have xi and ei becomes ai, aji, and ej. So what does this tells you? This tells you that once you do change of coordinate, xj delta is essentially xi, ai, aji. So this tells us that we actually got the change of coordinate formula. I'm just kind of do the derivation, right? So you have a actually probably easy, it's actually looks better. I should do this. Oops, sorry. AJI XI. Okay. So this is true for each J. This is the change of coordinate. Okay, so what this tells you, how do you change? So this is essentially for each coordinate of x delta, this is essentially the transition map, right? You plug in some x, output some x delta. And this relation, this transition map, you can see it's just a multiple of some matrix, right? And then adding up the multiplication. So this is definitely smooth, a smooth map. And as you can see, since this invertible matrix, you can easily find the other around, right? If you want to find the inverse map, like, which means if you want to represent x in terms of x delta, then you just essentially have the same formula, but now the matrix becomes inverse of A. So this kind of change of coordinate is definitely a bijection, right? The action is like 1, 1, and on 2. And on top of that, because if you plug in x, you come out with this x delta. This is just multiplied by some matrix. So this action is definitely a smooth map, right? And vice versa. So essentially, this tells you the transition map. I'm going to cut it short because I think I'm spending too much time on this example. So the transition map is diffeomorphism. You can easily see. So then if it's diffeomorphism, then they're smooth compatible. So this tells you it doesn't matter which basis you use, to identify V with Rn. The smooth chart that you come out with is going to be compatible anyway. So then once you collect all the possible compatible smooth like charts, then it will give you all the collection of all such charts will give you the smooth structure. And then once you have the smooth structure, then that's a smooth manifold. So I'm actually going a little bit detour way, very rigorous way to show you how we identify a finite dimensional vector space with Rn. And you can see it, this is done in a more rigorous way, right? But in some sense, you can see the structure is pretty much the same, right? You have V, once you choose one particular, doesn't matter which basis you choose, you have some coefficient, the coordinate, that essentially gives you identification between the vector space and the Rn. So that's why working with V is kind of like working with Rn. So you can imagine they should share the same structure. Okay, so before we move on, I just want to briefly introduce this notation. So this is what we call the Einstein summation. So people in physics, they probably already get used to about this notation. So this is actually very useful for geometry as well. You're going to see it a lot. So you can see that a lot of time when I need to do summation, I need to keep writing a summation. So there's one abbreviation that we use a lot of time is that instead of having to write down the summation, like sum from I equals 1 to n, I just use something like this, xiei. But how do I know when does it mean to have a summation? Then it's when the same index, for example, in this case, I, that appear exactly twice. And you can see that this is now why we choose the coordinate to be an upper index and a vector to be a lower index. This is a convention that geometers use a lot. So once you have a one upper and one lower index, once you see that, you automatically means that you're doing a summation. And the summation will be any summation. For example, if your index is I, say if I can run from 1 to n, then it just means you sum up from I equals 1 to n. You run over all the possible values. So from now on, probably sometimes I'm going to use this Einstein summation, and especially later on when we have so many different summation, you don't want to write like 5 summation index, right? And it can be very confusing. And so to have Einstein summation like this, you really need to have a upper lower index. Once I see that, then I know it's a summation. It's like a default convention we use. Okay, so is there any question? Sorry, so any questions? I'm going a little bit fast because this is some example that you can actually later on read it from the textbook. Okay, so another example that people see commonly is, I just want to introduce the notation here as well. If you see this capital M of M times N, M by N, and with R, this is essentially what we know of the space of any M by N matrices. And R stands for that you are having a real entries, okay? So then for the square matrix, we usually use this abbreviation. So it turns out that like this space, right, you can identify with, because you have M by N entry, right? So usually people identify it with R to the M times N, right? You can see that it's a M times N dimensional vector space, right? This is something we learned in linear algebra. And so basically you can see that this is a M times N dimensional smooth manifold. And another subset of this space is all the invertible square matrix, right? And usually we call it GL and R. This is, I mean, the formal definition is general linear group because it actually has a nice group structure. And all this invertible M by N matrix is actually an open set of some subspace. So actually you can think of this, all the invertible matrix, right? It's as if you can think of it as the pre-image of determinant map. If you think of determinant as plugging all the M by M entries, and determinant is just you taking all the summation or multiplication, right? It's a continuous map. And it's a pre-image of determinant map of all the real number but 0, right? Because invertible metric is actually whenever determinant is not 0, right? So all this invertible matrix, essentially the collection of it is the pre-image of some open set, right? So it's actually open. So it's an open set subset, actually. It's an open subset of n squared dimensional vector space, right? So it's an open subset which lies in the space of M by N matrix. So we just said if you have an open subset of some smooth manifold, it's going to be another smooth manifold of the same dimension. So that's why this GLN is actually a n squared dimensional smooth manifold. So we can kind of directly use it, right? Because it's an open subset of a finite dimensional vector space. Okay. And I'm not going to have time to do all the examples. So for example, in the textbook, they also already do the RPN using the coordinate charts we worked with earlier. And they also talk about the product manifold, right? If you have a whole bunch of smooth manifold, you do the product of it. And they also talk about matrix of full rank, right? And that's another open like submanifold. Okay, so I'm not going to have time to, I don't have time to do this. So please just read through the example. So also there's a level set. Okay, I want to skip it. I just want to show you that level set is another example, nice example for the smooth manifold. And I'm just going to give you a hint is that essentially what we use is the implicit functions theorem. So by implicit function theorem, if we define the space, the M, to be the preimage of some scalar number, and if your total derivative of this smooth map is not completely zero for all the value at the preimage, right? Then we can actually show that M is n minus one dimensional smooth manifold. And you might find this familiar. This is exactly the same example we did with level surface when we do it in curving surface, right? Remember, we need to check it's a regular value. Then the preimage of regular value of some differentiable map, it's going to be a regular surface. Remember that. So this is exactly the same. It's just generalized to higher dimension. Instead of regular surface, we're talking about smooth manifold, right? So basically, you can see that I want you to also compare with the level surface in the 720 course. It's exactly the same thing. Okay, you just change the to higher dimension in Rn. Okay, so this is also an example in the textbook. Okay, so another thing I want to talk about is smooth manifold chart lemma. So I copied down all the statement I provided because this is exactly the same as the textbook. I just need to explain it. Okay, so it turns out that if you think about how we check the smooth manifold, we always need to start from topological manifold, and then we check the compatibility, and so on, right? It takes a lot of time to first even to check whether what's the topology, right? And then we check topological manifold, and then we check the smooth structure, right? It turns out that there's a kind of, in some sense, a shortcut, right? Like sometimes it's hard to describe what's the topology used. So it turns out that if you give me a collection of a bunch of subsets and some map, if it satisfies the following 5 criterion, then we can actually show that all this criterion, all this collection of sets is going to give us a nice topology. And then, so we don't really need to directly check the topology, right? Because sometimes that you don't even know what's the topology used here. So basically the statement is the following, that if you give me a collection of subsets, okay, of M, let's call it U alpha, and a map, okay, I don't even know whether it's homomorphism yet. But if it satisfies the following 5 criterion, first of all this map is a bijection between U alpha and an open set. So they already tell you the image should be open in Rn, okay? And for all the index alpha and beta, this set phi alpha of the intersection of U alpha and U beta, and also under the image under phi beta is also open in Rn. And the third criterion says if the intersection of 2 sets is not empty, then the transition map is smooth. Okay, and since we don't care about the order, so essentially it tells you the transition map is diffeomorphism, right? And the fourth condition says you only need countable many U alpha to cover the whole subset, the whole M. And the last one is if you have distinct points in M, you can either find the same set U alpha containing both points, or you can find a disjoint U alpha, U beta such that you separate them. With all these 5 criterion, even though I didn't really explicitly tell you that M is a topological space at all, right? I didn't say anything about M. M is just a set. But if you can give me such collection, right? If you can find such collection which satisfy those 5, then I can actually tell you that M would have a unique smooth structure, meaning I'm going to use all this criterion to create a topology on it. And it's going to be a unique smooth manifold structure. And all this pairing of U alpha and V alpha is going to be a smooth chart. So you can actually see that why I can claim it's going to be a smooth manifold. First of all, you can see that I'm using this 5 criterion to replace Hausdorff, second countable, and locally Euclidean. You can already see some of them already tells you, right? So for example, the number 5 essentially should give you the Hausdorff, right? So of course, I need to convince you, create a topology to show you that U alpha is actually open. Once I can define the topology nicely, you can see that 5 actually tells you it's Hausdorff. What about 4? 4 tells you the second countability, right? Second countable. And you can see that the first 3 is going to help us to say that it's actually a homeomorphism. The phi is actually homomorphism, right? And also you can define a topology. And the third one, the third criterion actually tells you the smooth compatibility, right? Smooth compatibility. Because it tells you the transition map is a diffeomorphism. So you can see that some of them, you can kind of directly see that they replace some of the criterion of checking whether it's a smooth manifold, but it's actually more direct in some sense. Okay, so actually the only thing we need to do here is to define a suitable topology on this manifold. Okay, so you know what I'm going to do is, I want to move on to a little bit of the manifold with boundary, because I really want to get to the point. So I'm going to ask you to read this lemma, proof of lemma 1.35. And then on Saturday, if I have time, I will come back to prove it. Okay, so it's actually not that bad, but I feel like that within the next 7 minutes, I may not be able to say it nicely. But the next thing I want to do, the manifold with boundary, can be done quickly. So I'm going to just skip this for now. I will come back with the proof. But I would want you to read it first, because once you read it, you'll have a better sense. I feel like if I just tell you this, it's actually not easy to understand right away. So I'm going to move on to manifold with boundary. I may not be able to finish it. I will come back on Saturday. But as I said, this is very much the same as the usual manifold. So this is topological manifold with boundary. The original topological manifold is locally Euclidean, but this is not locally Euclidean anymore. So, which means you should be careful. Manifold, when we say manifold with boundary, it's not necessarily a topological manifold in the usual sense, in the original sense. All we can say is it locally looks like upper half space. And we use HN, the closed upper half space. What's an upper half space? It's essentially you have all the n coordinate, oops, sorry. But the last one is bigger than or equal to 0, right? So this is the picture I draw here, right? You have the upper half space. So it's not locally Euclidean anymore. So you cannot, unless boundary is empty. So manifold with boundary is not a topological manifold. At most, at this point, you can only say that it locally looks like an upper half space. Okay, then what's the difference? So there's this is the picture I can draw, like something. So imagine you have a surface like this, right? And it ends here. So you can see there's an opening here, right? Then you can see that I'm going to tell you that this open circle here is going to be my boundary, right? Intuitively, you can see this is the case. So how do I define a topological manifold with boundary? First, of course, you need to have a topological space, right? You start from a topological space. And I'm going to already assume, right, the Hausdorff and second countable is unchanged. I still need this two, right? So I still need this two criteria. But the only thing is now it's not locally Euclidean, right? It's not homomorphic to Rn, but rather it's homomorphic to some open set in Hn. Okay, so you're going to see there's two possibilities here. So first, let's see what's the definition. So N is a topological manifold with boundary if, I mean, this is to replace the locally Euclidean. If and only if for every point in the manifold, you can find an open neighborhood such that it contains the points, and you can find a homomorphism from this open neighborhood where the image is an open set either in Rn or now possibly in Hn. If it's an Rn, then it's the usual homomorphism, right? It's in the usual sense that we know of, but it's still possibly homomorphic to some open set in Hn. So you could possibly have two pictures like this. So first, if you have a point in M like this, you can always find an open set, right? This is U alpha, that's called U alpha. And it can get mapped to some open set here, right? This open set here is the usual open set, either you can say in Rn or Hn, right? So one type of open set in Rn is like this, which doesn't touch the boundary of Hn. What's the boundary of Hn? You will see that they use this notation. The boundary of Hn is when Xn is 0, right? When the last coordinate is 0, right? So the other possibility is if you, unfortunately, you might pick a point here, right? On the H in some sense, then you cannot have a whole open set like in the usual sense, right? Because that would be beyond the scope of your surface, right? So at best, you can only pick some open set like this, right? Nearby the point, but it's still and then the open set should contain this H as well, right? This is essentially homomorphic to an open set here, including the boundary here, right? And then your points get mapped to here, right? So why I know I can claim this is an open set in Hn, because if you put a subspace topology, right, you are in the giant Rn, right? So what's the open set in Hn? Then you essentially take any open set in Rn, intersect with Hn, right? So if you take an open set like this and you intersect with Hn, then all you see is really this kind of like a half ball, not necessarily ball, but like something like this, right? So this is actually a possible open set in Hn, which actually intersect the boundary, the Xn equals 0 line of the Hn, right? So you could have two possible situations now. That's why this is what makes manifold with boundary a little bit spatial. And with these two possibilities in mind, then we can actually talk about, I mean, if you want to distinguish, you can talk about two different types of charts. The first type is what we call the interior chart, meaning your image of the open set will actually either completely lies in Rn, right? Essentially, or actually the open set does not intersect with, this is probably more precise, does not intersect with the boundary. So this will be the first case. So this is interior chart, right? Means that you map to a complete, like the usual open set in Rn that we know of, right? Doesn't touch the boundary. But of course, you can possibly have boundary charts, meaning your image of open set would touch the boundary of Hn, right? Then basically that's what we meant the boundary chart here, okay? And you can imagine that if you have a point, got sent it to some point which lies on the boundary of Hn, then we call it boundary point and so on. Okay, so I don't want to drag everyone here. So I'm a little bit slow because I was trying to put more time on the vector space. But as I said, the manifold with boundary is actually not difficult at all because it's very, very similar to the original case. It's just this extra different type of open set that we need to deal with. So on Saturday, I'm going to definitely finish up what I haven't been able to finish today. So I'm going to finish up the chapter 1, the manifold with boundary, and I'm going to do very quick. So please do me a favor, like start reading it, and then I will be able to also start the chapter 2 to define what's a smooth map or smooth function. And as I said, it should be very similar to what you saw in curve and surface, where we define a smooth map from a surface. How we define it, how do we know it's a smooth map? It means that when you pull back from the surface to some R2s, to some chart, then the composition map is a smooth map. So this is exactly the same treatment as what you saw in curve and surface. So that's why like when we define the smooth map from a surface, from a regular surface in 720, we essentially intentionally to use the same definition, so it can be easily generalized to what we are going to deal with. Okay, so so as I said, I'm going to have a makeup lecture on Saturday, and if you can make it, please definitely it will be your benefit to make it. If not, it's okay. I understand that people have things to do on Saturday. Then you can watch the recording later on. And don't forget that the homework 1 is going to due tomorrow night. So, I mean, if you have any question between now and Friday, just let me know, right? If you still need to make an appointment to talk to me, please let me know. Okay, so you're free to go. Then I will see you on Saturday.
I actually had a question.
Yeah, sure.
Problem 17.
Say again, problem what?
17.
1.7.
The stereographic projection.
Let me see. Okay, so what's the question?
So the basic question I have with this one is for the sigma okay, hold on, sorry. Computing the transition map. Is it okay if I verify it? Did you get, or is it U over the magnitude of U squared?
I don't remember on top of that, but I think that rings the bell. I remember at some point I got something. I calculate so many things in between, so I don't remember exactly the map, and I don't have the solution right now with me. So, but I remember, yeah, it looks quite right. Yeah, let me just quickly eyeball. Can I eyeball the solution? So you just plug in sigma inverse and then plug into sigma. So let's see. So this is UN plus 1. 1 minus that. Looks like it though. This is UN plus 1, so I get 1 minus this bottom and 2 1. Oh, sigma delta, sorry. Sigma delta would be plus. Plus. Okay. Oh yeah, 2U squared, so 2. Okay. Yeah, so I got U over U squared norm. Yeah.
Nice.
Yeah. So that's the map. So and then because the domain you plug in, I'm pretty sure it already avoid the origin, like when u equals 0.
Mhm.
So yeah, so it's so this map is definitely like you can directly see it. It's going to be a smooth map, right?
Mhm.
And then you can check that the other round, like the inverse, right? You also need to check the inverse because you want to check that the transition map is actually a diffeomorphism, right? So you also need to show that the inverse of this map is also smooth, right?
Yes.
Yeah.
Sure. And then for part D, when you say that, like, show that the smooth structure is the same as the one defined, so are we just supposed to use proposition 1.17b, where it says two smooth atlases for M determine the same smooth structure if and only if their union is a smooth class? So we're just supposed to show that their unions are the same and then use the proposition?
Which proposition? 1.17.
17,
Let me see.
page 13.
Yeah, so essentially this is another way of saying that like how do you know the union is smooth atlas? Means that if you so let's say you have a group, let's say the standard atlas called group A, okay, and you have group B, right? How do you know the atlas A, the group A, create the same atlas as group B? Same structure as group B? Then what you need to do is you need to check whether essentially the charts in A is smoothly compatible with B, right? Because if it's smooth compatible, that means they should already be included in the maximal smooth atlas, right, in the structure. So let's say what's the example 1.31. So for the sphere, they have the standard structure. Let me see where's the example. So the one that either you can say the earlier example in 1.4, or if you can see the example 1.31, right? So you need to actually check that the smooth chart from the earlier example would be compatible with the one we create here, that we have here.
First, we need to make sure they're compatible with example 31.
Yeah. And then let me see. So let's see. So they already have all the information we need. Yeah, so they already have the sigma and sigma delta, right? Oops. Yeah, so first of all, you can see that that's assuming you already proved the part C, right? So then if you prove the part C, then that tells you that in this smooth atlas, sigma delta is already compatible with sigma, right? Because that's how they become a smooth atlas, right? Assuming you already check C. And in the earlier example, either you use after we do the 1.31, we already know all these phi I, phi j are smooth compatible with each other, right? Then in that sense, you only need to check one of the phi I and one of the let me see, do I need to only, I think we only need to check. What I want to say is that you only need to pick one from each chart. Okay, let me double check. So if that's the case, if this is smooth or not, and let's say I have, so let me write down what I want to say here. So give me a second. So probably this is, so can you see my screen?
Yep.
Okay, so in one group that's coded Atlas A, right? Or like a sigma. So this consists just two of them, right? Map. I just write down the map, right? And the other is the previous example where you have all this phi I, phi j, and all different kind of thing, right? The phi I j thing. So separately, they are already a smooth atlas, right? After you check the part C, right? So what's a smooth atlas means within the the atlas, these two already compatible with each other. And all the phi I, phi j, whatever number of I and j, they're already smooth compatible with each other, right? So in order to show that they define the same smooth structure, you want to see that it's essentially the same thing. We are in some sense also confirming the proposition, right? And so you can see that, okay, if you want essentially either way, you can say that the union of these two is you wanted to show it's smooth atlas, right? How do you check that? It's essentially you need to check sigma or sigma delta is smooth compatible with any of phi I or phi j, right? So if you want to put it together and still call it a smooth atlas, then sigma or sigma delta should be compatible with phi I or any other phi j, right? But you can also view it this way if you don't want to go through the proposition. What it really meant is why if I check this, then essentially it defines the same smooth structure. Remember what smooth structure is. Smooth structure is, it's the same as, like if you say smooth structure determined by one of the atlas, right? Let's say the standard one, right? It means the maximum smooth atlas containing this original atlas, right? So you essentially you want to say, okay, not only I want to include this smooth atlas, I want to include all possible other charts that's compatible with everything already in it. So do you agree that if I can show you that sigma or sigma delta is smoothly compatible in phi I, then sigma or sigma delta should be already included in my smooth structure of this atlas? Because we need to collect all of the past smoothly compatible one.
You said if we show that sigma and sigma
sigma or sigma delta is smoothly compatible with phi I and phi j, then by the definition of the smooth structure, because if they're compatible, then I should also including sigma and sigma delta into my maximum smooth atlas, right? So they should define the same smooth structure already. So that's all you need to show. But what I'm saying is that you don't actually need to check sigma, the transition map or the compatibility with sigma and all of them. You only need to pick one from each of the smooth atlas, right? Because mutually they're already compatible, right? So you can see, okay, let's say if I want to check, so I only need to check one, one pair, right? In some sense, right? So let's say if sigma and one of the I, right, is diffeomorphism, right? Okay, if this is true, what about others, right? Okay, so others, let's say if I want to check sigma delta with, I don't know, phi j, right? Inverse, sorry. But you can see that this can be written as, I want to do it with sigma, right? And then this will be identity, and I want to use I and phi j, right? And because I picked a completely different thing, right? So do you agree these are equal?
Yes.
Oh, sorry, here.
Yes.
No, yeah. Right? Because these are identity, right? But you can see that I'm going to bundle it this way. Oops, sorry, this one. So if you already check one pair, sigma composed with phi I inverse diffeomorphism, this particular transition map, then if you want to check any other possibility, you can just go back to this one, right? And then we already know within sigma delta, this is already smooth, right? Because the original compatibility within that original chart. And this one is the one we know, right? And this one is phi I and phi j is within that particular smooth atlas. So that's also smooth, right? So you're having smooth, composed, smooth, so that's smooth. So you essentially only need to check one particular pair. You don't need to check all of it, right?
Yeah.
So you depends on which one the coordinate is easier, which to be honest, I don't know. I don't have the idea on top of my head, like which one would be, because I mean, phi and phi j, they all look the same. Like, so you just need to pick one of them. It might make difference. Like, for example, if you pick phi to the n+1, something like that, like it might be like different because the look of sigma or sigma delta, I believe some pair would make the computation slightly easier, I believe. Yeah, so pick the one that will make the computation the easiest. Yeah, because you only need to check one pair. Does that make sense? Yeah.
It makes sense. I guess I'm a little confused about you saying checking, because when we just, like, for example, the sigma and then the phi inverse, and then I guess I really don't understand about checking, because you said that the first pair is smooth. Then
you need to check this is diffeomorphism. We don't know yet, right?
Oh, okay. And
yeah,
then
you need to check that.
Shows
Yeah.
diffeomorphism, then we can do that, and then we're done. Or,
yeah, because once you can say that this particular choices is diffeomorphism, then all the other parts, like, because we already know sigma and sigma delta is smooth, is compatible, and all the phi and phi j is compatible. So the only thing we don't know is whether the sigma group is compatible with the phi group, right?
Yeah.
So, but then what I say is you only need to check one particular pair, one particular choice, pick one that makes the easiest computation, because once you check one of the pair, the other, but you could still have the transition map like this, right? Maybe sigma delta composed with phi j inverse. But once you know the other pair is like this sigma and phi, let's say phi inverse is diffeomorphism, then you can reduce, in some sense, reduce other ones into something you already know. And then, yeah, and then it should be compatible. So you only need to, the only thing at this point, you only need to check one pair. But I'm not saying definitely check sigma compose phi inverse.
As an
yeah,
example.
yeah, as an example, yeah, just one choices. Yeah, because I mean, this might not necessarily be the easiest one. But I don't know on top of my head which one is the easiest. Yeah, because depends on the look of the expression of sigma or sigma delta. Maybe sigma delta is easier. I don't know. Yeah. So you want to pick C, but if you already pick one and you can actually easily compute it, then I don't think you need to change it, right? You can just pick, just pick one that you think it would not cost you like the most time. Yeah.
Yeah. Okay. And then so just kind of going back to C. So once I find the show that the inverse of like sigma tilde composed with the sigma inverse, that shows it's a smooth structure.
So what you mean part C?
Yeah.
So what you did there is you check this is smooth, right? That's the first thing. And then you also need to check the inverse of that, which will be sigma composed sigma inverse, right? You also need to check this is smooth map, right? So I think one of them you already did it. I think this one is the one you say it's U over U squared, right?
Yeah.
Yeah, and then I don't know what's this. You need to figure out, maybe the same, maybe not. So so the things that, yeah, once you check both of them are smooth, but yeah, and then yeah, and then and then because you already know the inverse exists, so it has to be bijection. So yeah, and then that means the atlas consists of these two map with the corresponding domain. It's going to be a smooth atlas because every member is compatible with each other. When I say every member, means two of them are compatible with each other. Yeah. And then once you have a smooth atlas, then by the proposition or the by proposition 1.17, we know that for each given smooth atlas, it will be contained in a unique smooth structure. So once you have a smooth atlas, you can actually have, we're kind of like a little bit sloppy. We say, okay, once you have a smooth atlas, you definitely can use this smooth atlas to define or determine a maxima smooth atlas, which is the smooth structure. But we're not going to describe what that is because it's actually hard to describe it. So usually people would say, oh, it's the smooth structure determined by this particular smooth atlas. Yeah. And you have the unique one. Yeah, that's what we proved earlier, like a while ago, that I actually do a very like detailed proof of, yeah. So yeah, so up to here, you're already done, because then essentially this smooth atlas would define a smooth structure. So then this, with this particular smooth structure, then that will give us a smooth manifold for the sphere. So you can see that essentially, before we do the part D, we don't know whether the smooth structure determined by this particular atlas will be the same as the one in the previous example. We don't know. But after doing part D, we realized that, oh, the two smooth structures are essentially the same. Yeah. But either way, with either smooth structure, let's say before we know they're the same, with either one, it's one smooth structure. So that just tells us, yeah, so essentially we can find some nice smooth structure. Then we can essentially say sphere is a smooth manifold, right? Because with all this smooth structure, we finally can make sense of how do you define, for example, smooth map from sphere to some other function, right? Because usually if you think about it back then, when you're trying to say you have a function from, say, Sn to R, most of the time you're going to need x, like n+1's coordinate, because that's the, before we know Sn is actually an n-dimensional manifold. But in some sense, you will see that you waste data here, waste a coordinate, because technically you don't, locally, you don't need to use n+1 coordinate to define, to describe sphere, because it's an n-dimensional manifold. It's locally homomorphic to some part in Rn, right? So you can locally, actually, you can use just n coordinate to define, to describe any point on Sn. So you don't, because the thing is that this is a better way to define it in terms of like, I don't know, computer science, then you essentially use one less storage, like memory storage in some sense. Yeah. So, and then in this way, it's more what we call intrinsic, like it's more back to the core of Sn. So, because if you need n+1 coordinate, that means implicitly you are putting Sn inside a bigger space, right? And you then there will be a question comes in geometry that, okay, is any property or things I want to check, does that depend on how I put the Sn inside R to the n+1, right? So there will be an ambiguity. If I stuck my sphere into R to the n+1 different way, would that affect anything I want to say later on, right? It's actually not a very good way to describe Sn. So instead of doing that, we just treat Sn as a manifold itself. Forget about the ambient space. We don't need the ambient space to describe the property of sphere. That's the whole point we want to learn Sn as a smooth n-dimensional manifold itself. So in some sense, we just say, okay, forget about how it put it in the larger space. We don't need that. Like a lot of property we need, we only need to care about Sn as itself. Yeah. So that's the whole thing. That's the whole point here. Yeah.
Okay. Nice. Thank you.
Okay, welcome. Any other questions? So, okay, so everyone just, all right, thank you. All right, thank you, Shane.
See you.
See you
Saturday.
on
Bye.
Saturday. Yeah, see you. Bye.